So you know that feeling, right? You're staring down a coding interview,
Yeah.
especially one that asks you to design a system from the ground up. It can feel like you need to cram a whole computer science degree into like an hour just to get your thoughts straight.
Yeah, it's intense. But what if there was a smarter way? What if you could immediately grasp the core architectural patterns, those crucial object-oriented programming principles, and the essential concurrency stuff that really impresses interviewers?
Without getting totally lost in the weeds of implementation details.
Exactly. And that's precisely our mission in this deep dive. We've pulled together a powerhouse collection of expert curated design insights. Think of it as your personal, highly concentrated pre-interview audiobook. We're going to distill the most important nuggets of knowledge from, gosh, dozens of common design problems.
Like an express lane to being genuinely well-informed and ready to tackle those low-level design challenges head-on.
You got it.
Absolutely. Today we're zeroing in on low-level design specifically for Java OOPs interviews. We're embarking on this extensive, pretty rapid journey through tons of common system design problems. We're focusing specifically on their low-level design in Java, all underpinned by object-oriented programming principles.
And just to be clear, this isn't about writing lines and lines of code right now. It's about dissecting the why behind the structure. It's about understanding how classes, methods, variables, and, their relationships all converge to form a robust, scalable system. That's what interviewers want to see.
Right, the thinking behind the code.
Precisely. And by the end of this deep dive, you'll have this really formidable mental toolkit. We'll quickly hit core OOP concepts: inheritance, composition, aggregation, polymorphism. Then we'll identify critical design patterns: singleton, strategy, observer, state, facade,
Command, builder, factory.
decorator, chain of responsibility, composite, mediator, the whole lot. And crucially, we'll pinpoint exactly where multi-threading, thread safety, and specific data structures become vital.
Explaining how they ensure robustness and why they're indispensable for real-world systems and, well, for acing those interviews.
Get ready for some pretty rapid-fire insights. Let's jump in. Hashtag tag tag main deep dive.
All right, let's kick things off with a real classic LLD challenge. The parking lot system. Designing a system that handles multiple vehicle types, different floors, maybe various payment methods. Where do we even begin thinking about the core architecture?
Yeah, it's a great starting point. For interviews, a good place to begin is identifying that central control point. Here, the parking lot entity itself often employs the singleton pattern.
Singleton. Okay, so only one instance of the parking lot.
Exactly. You enforce that with typically a private static final parking lot instance field and a public static synchronized parking lot get instance method.
Why is that significant here? What is it by us?
Well, it creates a single, consistent entry and exit point for the entire system. Think about managing global state, like overall occupancy or total revenue. It simplifies that. It also often acts as a facade.
A facade, meaning it simplifies the interface.
Right. It provides a simpler way to interact with what might be complex internal processes, like vehicle entry, finding a spot, handling exit, and billing. Hides the complexity.
Okay, so the parking lot is the main coordinator, the front door. How do we model its relationship with the components inside, like the floors and the individual parking spots?
Good question. We often use strong composition. The parking lot has a compositional relationship with parking floor and ticket. This means floors and tickets are integral parts. They can't logically exist without the parking lot.
Right, they belong to it.
Exactly. And similarly, parking floor has a composition with parking spot. Spots belong to a floor.
Makes sense. What about the vehicles themselves? Cars, bikes?
For vehicles, car, motorcycle, truck, these demonstrate inheritance from an abstract vehicle class. This gives you code reuse for common stuff like license plates and enables polymorphism, so you can treat different vehicle types uniformly when parking them.
Got it. And the ticket, how does it relate to the vehicle and the spot?
The ticket shows aggregation with vehicle and parking spot. Has a relationship. The ticket references them, but it doesn't own their life cycle. The vehicle and the spot can exist independently of a specific ticket, right?
Ah, okay. Aggregation, not composition there.
Mm-hmm.
Makes sense. Now, thinking about a real parking lot, cars are coming and going all the time simultaneously. How do you handle thread safety? Prevent chaos?
Concurrency is absolutely paramount here. You can't ignore it. Inside the parking floor class, methods like find end park and release spot should be explicitly synchronized.
So locking the parking floor object itself.
Yes. That ensures only one thread can modify its state, like the list of available spots at any given moment, prevents race conditions where two cars might try to grab the same spot.
What about the data structure for available spots?
Good point. You'd probably use something like concurrent link deck for available spots. It's a thread-safe queue implementation, great for LIFO or FIFO spot management without needing manual locking on the collection itself.
And the parking spot doesn't need anything special.
Yes, for parking spot, the park vehicle variable is often marked volatile.
Volatile. Refresh my memory on why that's key here.
Volatile guarantees visibility. It ensures that any right to park vehicle by one thread, say, the thread parking a car, is immediately visible to all other threads checking that spot status. Prevents reading stale data.
Okay, crucial for accurate occupancy status. What about the money side? Billing and pricing.
Right. To follow the single responsibility principle, SRP, we typically introduce a separate billing service. Its only job is financial calculations. Decouples it completely from the parking logic.
Clean separation and pricing models. Hourly, daily.
That's where iPricing strategy comes in, implementing the strategy pattern. This allows you to plug in different pricing models, hourly pricing strategy, daily pricing strategy, maybe a weekend special without touching the billing service. Super flexible.
Nice. And the ticket itself, any special properties?
The ticket object should be designed as an immutable DTO, a data transfer object.
Immutable, meaning its state can't change after creation.
Exactly. Once a ticket is created with its entry time, vehicle info, spot info, etc., that data cannot be accidentally altered by some other part of the system. This ensures data consistency, which is critical for accurate billing.
Got it. Immutable DTO for the ticket. Okay, let's move on. Let's ascend to the elevator system. We're designing a system to manage multiple elevators in a building. Focuses on a central controller and independent elevator operation. How do we make sure concurrent button presses are handled smoothly?
Okay, elevator system. This one heavily leverages the singleton and mediator patterns. The elevator controller is usually a singleton, one central brain, and it acts as a mediator.
Mediator, meaning it sits between things.
Precisely. It decouples the button presses, internal or external, from the elevator cars themselves. When you press a button, it doesn't directly talk to an elevator. It sends a request object to the elevator controller.
And what does the controller do with these requests?
It places them into a blocking queue, often called request queue. This is vital for thread safety.
Why blocking queue specifically?
Because blocking queue safely handles concurrent producers, buttons adding requests, and consumers, elevators taking requests. It automatically handles the waiting. If the queue is full, the button thread waits. If it's empty, the elevator thread waits. Prevents the main application thread from blocking.
Ah, clever. So the blocking queue is like the central nervous system managing incoming requests. What about the structural relationships? How do the parts fit together?
Structurally, the elevator system class would have a composition relationship with elevator, car, and building floor. Elevators and floors are integral dependent parts. An individual elevator car maintains an association with request objects. It processes specific requests to move to certain floors.
And bus.
We also see inheritance there. Internal button inside the car and external button on the floor would both inherit from an abstract button class. Good for code reuse for common button things like a press method.
Makes sense. Now, how do we ensure each elevator operates independently and, adapts its behavior based on whether it's moving, idle, or has its doors open? That seems complex.
Right. This is where multi-threading and the state pattern really come into play. Each elevator car is designed to run on its own thread. Usually, it implements runnable and has a public void run method.
Own thread. So they operate completely independently.
Yes. This allows for parallel operation and responsiveness. If one elevator is slow or stuck, it doesn't halt the entire system.
And the changing behavior, moving, idle.
That's the state pattern. You'd have an elevator state interface with concrete implementations like moving up state, idle state, door open state. The elevator car acts as the context. It holds a reference to its current state object.
And behavior changes based on the current state object.
Exactly. Actions like move or open door are delegated to the current state object. This elegantly avoids massive if-else or switch statements based on some status enum, makes the code much cleaner, more extensible, easier to maintain.
That sounds way better than a giant switch statement.
Yeah.
And the request object itself.
The request object, like the ticket earlier, is best designed as an immutable DTO. Once a request, like go to floor 5, is created, its details remain consistent.
Okay, state pattern and immutability. Got it. Moving from vertical movement to efficient data management. Let's talk about the LRU cache, another classic interview question.
Hmm.
Designing a least recently used cache, it needs to kick out the oldest item when it hits capacity. What's the optimal data structure approach here?
Right, LRU cache. The most efficient implementation, the one interviewers usually look for to get that O1 time complexity for both get and put. It combines two fundamental data structures.
Okay, what are they?
You use a hash map for super fast lookups. Given a key, you find the item instantly, O1. And complementing that, you use a doubly linked list.
Doubly linked list. Why that specifically?
Because it lets you track recency perfectly and manipulate the order in constant time. When an item is accessed, get, or added, put, you move its corresponding node to the front of the list. The front always represents the most recently used item.
Eviction.
When the cache hits capacity, you simply remove the node from the tail of the list that's the least recently used item. Both moving to front and removing from tail are O1 operations in a doubly linked list if you have direct access to the node, which the hash map gives you.
So the hash map stores the key and a reference to the node in the doubly linked list.
Precisely. That's the link between them.
Okay, so the list nodes are internal components managed by the cache. How do these classes formally relate in OOP terms?
Right. The LRU cache class has a strong composition relationship with the node objects. These nodes are the elements of the doubly linked list, and they're entirely managed and owned internally by the cache. They don't exist independently outside it. Each node typically holds the key, the value, and pointers to the previous and next nodes.
Makes sense. Now, caches are often hit by many parts of a system concurrently. How do we guarantee thread safety? Prevent multiple threads messing up the cache state when they get or put at the same time?
Concurrency control is absolutely critical for a cache to be reliable. You can't have multiple threads corrupting the linked list structure or the hash map. The get and put methods of the LRU cache need explicit locking. A common approach is to use a reentrant lock.
Reentrant lock, why that instead of just synchronized methods?
Reentrant lock offers more flexibility and potentially better performance under high contention compared to just synchronizing the entire methods. It allows for more fine-grained control. You'd typically acquire the lock using lock.lock at the start of the critical section where you modify the map and list, and ensure it's always released using lock.unlock in a finally block.
Okay, finally block is key there to prevent deadlocks if something goes wrong.
Absolutely. This lock prevents race conditions where two threads might, say, try to move the same node or evict different nodes simultaneously, leading to an inconsistent cache state.
That's a robust way to handle it. Are there any, simpler alternatives that might come up, maybe something built in?
Definitely good to be aware of Java's built-in linked hash map. It's a very practical alternative. You can actually configure linked hash map to behave like an LRU cache.
How do you do that?
In its constructor, you pass true for the access order parameter. This tells it to order elements based on access time, not insertion time. Then you just need to override the remove eldest entry method. This method is called after a put, and you implement your logic there to return true if the cache size exceeds capacity, causing the eldest entry, the LRU one in access order mode, to be removed.
Ah, neat. So linked hash map can do LRU out of the box with a bit of configuration.
Pretty much. While it might not offer the same level of granular lock control as a custom reentrant lock setup, it's often simpler and perfectly good enough for many situations. Showing you know about it demonstrates practical Java knowledge.
Good to know. Okay, let's transition to entertainment with the movie ticket booking system. We're designing a scalable system for movie listings, showtimes, seat selection, booking. Quite a lot going on. What's the overall structure look like for something this complex?
Yeah, it's a good one. The booking system itself often functions as both a singleton and a facade.
Singleton again for central control and facade to simplify things.
Exactly. As a singleton, it's the single global access point. As a facade, it hides the complexity of dealing with separate services, like maybe a movie service, a theater service, and the actual booking service. It delegates tasks to them.
Makes sense. How about the physical structure? Cities, cinemas, halls, seats.
We typically model that using strong composition to represent the real-world hierarchy. A city is composed of cinemas, a cinema is composed of cinema halls, and a cinema hall is composed of seats. This creates a clear ownership structure and a natural containment hierarchy, which is really helpful for navigating the system and ensuring data integrity.
Okay, clear hierarchy. Now, what about the relationships between the movies playing, the specific showtimes, and the bookings users make?
Right. A show, a specific screening, would have an aggregation relationship with movie and cinema hall.
Aggregation, not composition.
Yeah, because a show references a movie and a cinema hall, but it doesn't exclusively own them. The movie exists independently, the hall exists independently, the show just links them for a specific time.
Got it. And the booking itself.
A booking object then forms an association with a user, a specific show, and a list of seats. It ties all these distinct entities together for that one reservation.
Okay. And payments.
The booking class would likely interact with a payment service. And that service would use an iPayment strategy interface, that's the strategy pattern again, allows you to easily plug in different payment methods, credit card, PayPal, gift card, whatever.
Flexibility through strategy.
Yeah, it's
Nice. Now, the big one for movie tickets, concurrency. Multiple users trying to book the exact same seat at the exact same time. How do we prevent race conditions during seat selection?
This is where fine-grained locking is absolutely crucial. You definitely don't want to lock the entire show object when someone tries to book. That would kill concurrency.
Right. Everyone trying to book for that show would block.
Exactly. So instead, the booking service might use something like a seat lock provider. This provider manages temporary locks, maybe re-entrant locks, but on a per-seat basis.
Locking individual seats.
Yes. When a user starts the booking process for specific seats, the system tries to acquire the locks for just those seats. If it gets the locks, great, proceed to payment. If not, it means someone else is holding the lock, booking that seat, so you tell the user it's unavailable.
That sounds much more scalable. It only locks what's absolutely necessary.
Precisely. It's far more realistic for handling high traffic and prevents race conditions effectively, ensuring only one booking process can secure a particular seat at any moment.
And the seat object itself.
Like many of these data carriers, seat should be an immutable DTO. Its property's row number, seat number within the row shouldn't change after it's defined. Ensures consistency.
Immutable seat DTO per seat locking. Key takeaways there. Okay, from movies to marketplaces, let's explore the e-commerce website. Coreflow.search. Add to cart. Place order. What are the fundamental building blocks here structurally?
Okay, e-commerce. We typically start with an inheritance hierarchy for user, maybe an abstract user with concrete classes like customer and admin, sharing common properties but having different capabilities. A customer then usually has a composition relationship with shopping cart and maybe address. The cart and address are integral, owned parts of that customer's profile or session.
Cart belongs to the customer. Got it. What about orders and products?
An order similarly has a composition with order items. The items are the order, essentially. Product and product category often have a many-to-many association. A product can be in multiple categories. A category holds multiple products. This is often managed via a linking table in a database.
Right. And notifications, order confirmation emails, shipping updates.
That's a prime candidate for the observer pattern. The order object acts as the subject. When its status changes, e.g. placed, shipped, delivered, it notifies all registered observers. These observers might be implementations of a notification service like email service, SMS service, via an iOrder observer interface. Ensures everyone who needs to know gets updated automatically.
Decoupled notifications via observer. What about payments and maybe other patterns?
Again, iPayment Strategy implements the strategy pattern for flexible payment methods, very common in e-commerce. And while maybe not detailed everywhere in the sources, the factory pattern could be really useful for creating different types of users, customer versus admin, or maybe different complex product subtypes, keeping the creation logic separate and clean.
Okay. Now, e-commerce sites get hammered with traffic, especially during sales. Concurrency is critical. How do we ensure thread safety, particularly for inventory and the shopping cart itself?
Absolutely critical. The inventory service is often a singleton, one central place managing stock levels. And for thread-safe stock counts, it often uses atomic integer.
Atomic integer, why that instead of just synchronizing the methods?
Atomic integer performs atomic operations like increment and get or compare and set very efficiently, often using low-level hardware instructions. For simple counters under high contention, it can perform better than locking an entire method with synchronized. It manages the reserve stock and release stock operations safely.
Okay, atomic updates for stock. What about the user's shopping cart?
The shopping cart's methods that modify it, like add item, update item quantity, remove item, should generally be synchronized. Why? Because it's usually tied to a user session, and you could have concurrent requests from the same user, maybe rapid clicks or multiple tabs, that could lead to inconsistencies if not synchronized.
Gotcha. Synchronize the cart operations. Anything else crucial?
Yes, a really important one. Order item must be an immutable DTO. And crucially, it needs to store the price, purchase the price of the item at the moment it was added to the order.
Why is that so vital?
Because the product's price in the catalog might change after you add it to your cart, but before you check out. Storing the price at purchase ensures the order total is correct and the historical order record is accurate. Huge for financial integrity.
Ah, yeah, that's a subtle but critical detail. Immutable order item with price at purchase. Okay, let's hit the road with the ride-sharing service. Think Uber or Lyft. Core job: match riders with drivers, manage trips, calculate fares. How do we structure this?
Right, ride sharing. We usually start with inheritance. Rider and driver both extend an abstract user class, share common stuff, but have specialized roles. A driver typically has a composition relationship with the vehicle. In this context, the vehicle is intrinsically tied to that driver. A trip object then forms an association between a rider and a driver, linking them for that specific journey.
And the system coordinating all this, the matching.
That's the ride dispatch system. It often acts as both a singleton, one central coordinator, and a facade mediator. As a facade mediator, it simplifies the complex process of finding nearby drivers, offering rides, handling acceptance, and managing the trip lifecycle. It decouples riders and drivers from the nitty-gritty dispatch logic.
Okay, and fares.
Yeah.
Standard surge pricing.
That screams strategy pattern. An iFare strategy interface allows you to plug in different calculation models. Standard fare strategy, surge pricing strategy, maybe airport fee strategy. Makes pricing logic flexible and easy to update.
Strategy for fares. Makes sense. Now, location is obviously central here. Driver locations are constantly changing. How are they managed safely in a concurrent environment?
The location service is key. It needs a thread-safe way to store and update driver locations. A concurrent hash map mapping driver ID to location is a very common and efficient choice.
Concurrent hash map again. Why is it so good for this?
Because it allows concurrent reads and, importantly, concurrent writes, updates to driver locations, without needing to lock the entire map for most operations. It provides fine-grained locking internally, which is great for performance when you have many drivers updating their location frequently.
Better performance than just synchronizing everything. What about managing the trip itself? Start and cancel.
To keep things clean SRP, you'd often introduce a separate trip service. Its job is solely managing trip state transitions, create trip, assign driver, start trip, end trip, cancel trip. Separates that logic from the dispatch matching system.
Good separation.
Yeah.
And how do we track states?
We use enums like driver status, available, on trip, offline, and trip status, requested, accepted, in progress, completed, canceled. Enums make the states type safe and the code much clearer.
And the location object itself, mutable or immutable.
Location with latitude, longitude should be an immutable value object. Once created, its coordinates don't change. This prevents accidental modification and makes it inherently thread-safe to share.
Immutable location. Got it. Okay, from ride sharing to rentals. Let's look at the car rental system. This covers managing vehicle inventory across different locations, handling reservations, and billing. What are the key entities and relationships here?
The rental system often acts as the main facade, simplifying interactions for the customer. It would have a composition relationship with rental locations. Locations are part of the system. Each rental location, in turn, would likely have a composition with its vehicle inventory. The inventory belongs to that specific location.
And the vehicles within the inventory.
The vehicle inventory holds an aggregation of vehicles. This is a key distinction.
Aggregation, why?
Because the vehicles themselves, the actual cars, can logically exist independently of a specific inventory at a specific moment. They might be moved between locations or exist before being assigned to one. So the inventory aggregates or collects vehicles, but doesn't strictly own their entire life cycle in the same way a parking lot owns its parking floors.
Ah, subtle difference. Okay. And vehicle types.
Vehicle would be an abstract base class with an inheritance hierarchy. Car, SUV, truck, extending it. A reservation then forms an association linking a customer, who is a type of user, to a specific vehicle for a period.
And payments, pricing.
Again, iPayment strategy using the strategy pattern for flexible payment options. And the factory pattern could be useful here too, maybe for creating different vehicle objects based on type when adding new cars to the fleet.
Makes sense. Now, vehicle inventory is definitely a shared resource. Multiple customers trying to reserve cars, potentially the same car category at the same location. How do we ensure thread safety for availability?
This is a critical concurrency point. All methods within vehicle inventory that change its state, specifically things like add vehicle, reserve vehicle, decrementing availability count, and marks available, incrementing count upon return, must be synchronized.
Synchronize all those inventory modification methods.
Absolutely. This ensures that only one thread can modify the inventory state, like the count of available SUVs at a time. It prevents race conditions like two users simultaneously reserving the last available SUV, leading to an overbooking. Failure here is a major business problem.
Right. Double booking would be bad. Any other structural points?
A reservation service could be introduced to handle reservation logic specifically. SRP would use a vehicle status enum, available, reserved, rented out, maintenance, for type-safe tracking of individual vehicle states. And you guessed it, reservation should be an immutable DTO once confirmed.
Immutable reservation. Okay, pattern emerging there. Let's move to the ATM system. Modeling an ATM's interaction with the user and the bank. Focus here seems to be on state management and transactions. What patterns are key?
The ATM class itself is a prime example of a facade. It provides that simple, user-friendly interface, insert card, enter PIN, select withdraw, etc., hiding all the internal machinery. It has a strong composition relationship with its hardware components, card reader, keypad, screen, cash dispenser. These are integral parts.
And the flow. Inserting card, entering PIN, selecting options.
That's where the state pattern absolutely shines. The ATM holds a reference to its current state, which is an object implementing an ATM state interface. You have concrete states like idle state, hash card state, authenticated state, transaction in progress state. The ATM's behavior completely changes based on which state object is currently active.
So instead of if status IDLE, the behavior is in the state object.
Exactly. Methods like insert card or enter PIN are delegated to the current state object. The idle state might accept a card, but the hash card state would reject it. It makes the logic incredibly clean and easy to add new states or modify behavior without touching the main ATM class much.
Very elegant. What about the actual transactions? Withdraw, deposit.
For that, the command pattern is often used. An iTransaction interface represents a command with concrete implementations like withdrawal command, deposit command, balance inquiry command. These command objects encapsulate the request itself. This decouples the ATM, the invoker, from the specific execution logic of each transaction type. You can easily add new transaction types later.
Command pattern for transactions. And talking to the bank.
You typically have a bank service interface acting as a facade or proxy to the actual back-end bank systems. It hides the complexity of network communication, authentication with the bank, etc.
Okay, state, command, facade. Powerful combination. How is thread safety ensured, especially for the critical part, giving out cash?
Right. The cash dispenser's dispense amount method must be synchronized. This ensures the physical act of counting and dispensing notes is atomic. Prevents scenarios where concurrent operations might lead to dispensing the wrong amount or corrupting the internal count of available cash.
Makes sense. What about other details?
The card object holding card details would be an immutable DTO. You might have a coin enum with associated values if it handled coins, and a separate cashbox class could manage the internal cash levels, SRP.
Immutable card, synchronized dispenser. Got it.
Ooh.
Okay, moving to communication systems. The notification system. Designing something scalable and flexible for sending notifications through various channels, email, SMS, push.
The core pattern here is strategy. The notification service uses an I-channel interface. Concrete implementations like email channel, SEMS channel, push channel provide the specific logic for each delivery method. This allows the notification service to send via any channel without knowing the specifics. You can easily add new channels later just by creating a new class implementing iChannel.
Strategy for delivery channels. What about creating the notification itself? They can have lots of parts, recipient, subject, body, maybe attachments.
Exactly. For a complex object construction like that, the builder pattern is a great fit. You'd have a notification builder class. You use the builder to set the different parts step by step, .2os recipient, .subject, sub.body, msg.build, and the final build method creates the validated notification object. Ensures you don't forget required parts.
Builder for complex creation. How do the parts relate?
A notification object would have a composition relationship with its recipient and message content. These are essential parts of it. You might also see a channel factory acting as a factory singleton. Its job is to provide instances of the different iChannel implementations, potentially reusing them, like a single email sender instance, for efficiency.
Factory for channels? Anything else?
The source material also mentioned the decorator pattern could be used to add extra features like logging around notification sending or maybe adding priority handling without modifying the core channel logic. Wraps additional functionality around the channel object.
Decorator for enhancements. Now, a notification system could easily become a bottleneck if sending takes time. How do we ensure high throughput? Make sure it doesn't block the main application.
Absolutely critical point. The notification service must send notifications asynchronously. It explicitly uses an executor service, usually configured as a thread pool. When send notification is called, the service submits the task, sending the notification via the chosen channel, to the thread pool and returns immediately.
So the caller doesn't wait.
Correct. The caller isn't blocked waiting for the email to be sent or the push notification to be delivered. The thread pool handles the actual sending in the background. This is essential for high-throughput systems.
Asynchronous delivery via thread pool. And the notification object.
Should be immutable. Once created by the builder, its content, recipient message, etc. shouldn't change. Ensures consistency as it passes through the system.
Immutable notification. Okay, next up, the logging framework. Inspired by tools like Log4 or Logback, how is this structured architecturally?
Logging frameworks often use the chain of responsibility pattern. Loggers typically form a hierarchy, pre-UG, com.myapp.service is a child of com.myapp. A logger usually has an optional reference to a parent logger. When a log event occurs, it can be processed by the current logger and then passed up the chain to its parent, allowing for cascading handling or filtering at different levels.
Chain of responsibility for log event propagation. What about where the logs go and how they're formatted?
That's where the strategy pattern comes in again, twice. iAppender is an interface defining output destinations, strategies for output. Concrete appenders like console appender, file appender, database appender implement this. A logger has a composition of appenders it can log to multiple destinations. And iLayout is an interface defining message formatting, strategies for formatting. Implementations like pattern layout with customizable patterns or JSON layout format the log event before it's written by the appender. An appender usually has a composition with a layout.
Two strategies, appender and layout. Who manages the loggers?
There's usually a log manager implemented as a singleton, which acts as both a factory to get or create logger instances by name and a registry for managing the overall logging configuration.
Singleton log manager acting as factory registry. Now, many parts of an application log concurrently. What are the critical thread safety considerations?
This is vital for reliability. The concrete appender implementations, console appender, file appender, network appender, etc., must be thread safe.
Why is that so important?
Because multiple application threads will be calling log concurrently, and those calls eventually reach the append method of the same appender instance, for example, writing to the same file. Without proper synchronization, either synchronized methods or internal locks within the appender, you could get corrupted log files, interleaved messages from different threads, or even lost log messages. It has to handle concurrent writes safely.
Okay, appenders must be thread safe. What about the log event itself?
The logging event object, which carries all the information, timestamp, level, message, thread name, logger name, should be an immutable DTO. Once created at the point of the log call, its details shouldn't change, ensuring integrity as it flows through the system.
Immutable logging event and log levels.
Log level is an enum, debug, infofo, warn, error, fatal, defining verbosity levels for type-safe control over what gets logged.
Got it. Chain of responsibilities, strategies, singleton, and thread-safe appenders. Now for the chat application, think WhatsApp or Slack. Real-time messaging, different chat types, private, group, message delivery. What's at the core?
The chat server is usually the central hub. It heavily uses the observer pattern to notify users in real time when new messages arrive in chats they're part of. It's also typically a singleton, one server instance, and acts as a mediator. It routes messages between users and chats without them needing direct references to each other, decouples users and chats.
Observer, mediator, singleton server. What about different kinds of chats?
You'd use inheritance. Private chat and group chat would inherit from an abstract chat class, sharing common functionality but having specific logic. Example, group chat needs to manage multiple members. There's a many-to-many association between user and chat. Users can be in many chats, chats can have many users.
And the messages within a chat.
Chat has a composition of messages. The messages are integral parts of the chat's history. Message itself could also have its own inheritance hierarchy, like text message, image message, voice message, for different content types.
Makes sense. Real-time chat generates a lot of data. Persistence is key for history. How's that handled? And managing those live connections.
Right, you need dedicated components. A message store layer handles persistent saving and retrieving chat history. This often involves interacting with a database, maybe a NoSQL one like Cassandra that's good for write-heavy workloads. And a connection manager handles the complexity of user sessions and the real-time connections themselves, UGC, WebSockets. It manages who's online, their connection status, and how to push messages efficiently. This separates the networking concerns from the core chat logic, SRP.
Okay, separate persistence and connection management. How does the observer pattern work in practice here?
The user object would implement the observer contract, maybe an iUser observer interface with a receive message method. When the chat server gets a message for a chat, it looks up the online users in that chat and calls received message on each of them via their connection managed by the connection manager.
Got it. And the message object?
Immutable DTO, naturally. Once a message is sent, its content, sender, timestamp, etc. should not be alterable. Preserves the integrity of the chat history. We might also have user status and message status enums.
Immutable message. Okay, next, a fundamental pattern. The publish-subscribe system, maybe a simplified Kafka or Kafka-lite, asynchronous communication. What patterns jump out immediately?
This system is the observer pattern, pretty much directly implemented. A topic acts as the subject, or observable. iSubscriber implementations are the observers. When a message is published to a topic, all its registered subscribers get notified. The broker, the central server managing topics, has a composition relationship with topics. Topics are created and managed by the broker.
And the publishers and subscribers.
iPublisher and iSubscriber are defined as interfaces. This is crucial for loose coupling. Producers, publishers, don't need to know about specific consumers, subscribers, and vice versa. They only interact with the broker via these interfaces. The broker itself often acts as a singleton facade. Singleton for central control, facade to provide a simple interface, publish, subscribe, create topic, to the outside world.
Straightforward observer implementation. What about the nitty-gritty design details and concurrency? PubSub needs to be robust and handle many messages.
Right. Inside the topic class, you typically find a blocking queue message to hold incoming messages from publishers. Blocking queue provides thread-safe handling of concurrent publishes. Now, for a more advanced system like Kafka, the topic also needs to track consumer progress, especially if you have consumer groups. It might use something like a map string, atomic integer, offsets by group.
Offsets, what are those for?
An offset tracks how far a specific consumer group has read within the topic's message stream, or partition. Using atomic integer allows for thread-safe updates to these offsets as consumers acknowledge messages. This lets consumers resume from where they left off if they restart.
Essential for fault tolerance. How do messages get from the topic to the subscribers?
Often, the topic or a dedicated dispatcher component would have a worker thread, maybe in a dispatch messages method. This thread continuously pulls messages from the blocking queue and pushes them out to all currently registered and active iSubscribers for that topic.
And the message payload?
Again, designed as an immutable DTO. Once published, its content should not change, ensuring message integrity as it flows through the broker to potentially many subscribers.
Immutable message. Okay, let's move to a Q&A platform like Stack Overflow. Key entities, relationships, content structure. How does this look?
Stack Overflow has several important inheritance hierarchies. You'd likely have an abstract content class, inherited by question, answer, and comment. They share common things like author, timestamp, score. Similarly, an abstract user class could be inherited by member and moderator, giving them different permissions and roles.
Makes sense.
Okay.
How's the content structured? Questions, answers, comments.
Question has a strong composition relationship with its answers. Answers belong to a question, and both question and answer are composed of comments. Comments belong to a specific question or answer. This reflects that nested discussion structure perfectly.
Nested composition. What about tags?
A question has a many-to-many association with tag. Questions can have multiple tags. Tags can be applied to multiple questions.
In the life cycle of question, open, closed, on hold.
That's a great use case for the state pattern. The question object acts as the context. It holds a reference to its current question state, e.g., open state, closed state, on hold state. Actions like add answer or close would be delegated to the current state, which decides if the action is allowed.
State pattern for question lifecycle. Cool. Now, Stack Overflow is all about voting and reputation. How's that handled safely? Lots of people voting concurrently.
You'd definitely introduce a dedicated voting service for SRP. It encapsulates all the logic for casting votes and updating user reputations. The vote, user-intented, vote type, method within that voting service must be synchronized.
Synchronized vote method. Why is that essential?
To prevent race conditions, imagine two users upvoting the same answer simultaneously. Without synchronization, both threads might read the current score, both increment it, and both write back the same incremented value, resulting in only one vote being counted instead of two. Synchronization ensures these updates are atomic.
Critical for accurate scores and reputation. Any other structural elements?
You might have an abstract post-class or interface that both question and answer implement, reducing duplication for things like handling votes or comments. And you'd use enums for things like vote type, upvote, downvote, and question status, open, closed, on hold, for type safety and clarity.
Good use of enums. Okay, let's check out the library management system. Core operations: issuing, returning books, managing reservations.
The main library class often acts as a facade, providing a simple interface, borrow book, return book, search catalog, to the user or librarian, hiding the internal complexity. You'd have inheritance with member and librarian extending an abstract user class. Now, a really crucial distinction here is between book, the logical entity, like the Hitchhiker's Guide to the Galaxy, and book item, a specific physical copy with a unique barcode.
Ah, the abstract concept versus the physical thing.
Exactly. Book has a one-to-many composition with book item. The physical copies belong to the abstract book title. This is key for tracking individual copies.
What about reservations? If all copies are out, how do members get notified when one comes back?
That's the observer pattern. The book, the logical entity, acts as the subject. Members who have placed a reservation act as observers. When a book item associated with that book is returned, the book object notifies its registered observers, waiting members, via maybe an on-book available book item method.
Observer pattern for availability notifications. And searching the catalog.
You'd likely have a search service that uses the strategy pattern via an iSearch strategy interface. Implementations like search by title, search by author, search by ISBN allow for modular search logic.
Strategy for search. Now, managing those physical book items, checking them out, returning them, thread safety concerns.
Yes, the book items checkout, membered, and return book methods need to ensure atomic updates to its status, RG from available to loaned. In a system where multiple librarians might be processing checkouts returns concurrently, these methods should be synchronized on the book item instance. This prevents race conditions where two librarians might try to check out the same physical copy simultaneously.
Synchronize operations on the specific book item.
Got it.
And tracking status.
A book status enum, available, loaned, reserved, lost, manages the state of a physical copy clearly and safely.
Makes sense. Let's turn to a simpler but very illustrative example. The vending machine. Often cited as a prime example of the state pattern, right?
Absolutely. It's almost the textbook example. The vending machine is the context for the state pattern. Its behavior, whether it accepts coins, insert coin, lets you choose an item, select item, or dispense item, changes completely based on its current state. You have state objects like no coin state, has coin state, sold state dispensing, sold out state. Each state encapsulates the behavior allowed in that state.
So no big Eiffel's block checking the status.
Exactly. The vending machine just delegates the action to its current state object. The no coin state handles insert coin, transitions to has coin state. The has coin state handles select item, transitions to sold state, and so on. Super clean and extensible.
Very cool. And the vending machine itself to the user.
It acts as the facade. The user just interacts with simple methods, insert coin, press button, without needing to know about the internal states or inventory management. Internally, the vending machine has composition with its inventory and cash box, and the inventory is composed of item slots, each holding a specific item type and count.
Okay. What are the key design details in any thread safety aspects? Could multiple people interact somehow? Unlikely maybe, but good to consider.
A nice detail is using a coin enum, which should crucially include the value associated with each coin type, nickel 0.05, dime 0.10, quarter 0.25, makes handling money type safe. You'd have a cash box class responsible just for managing the current balance inserted and making change, SRP.
And inventory. What if two mechanisms tried to dispense the same item slot?
Right. The item slot's decrement count method, called during dispensing, must be synchronized. This prevents a race condition, however unlikely in a simple machine, where concurrent operations might try to dispense the last item, leading to an incorrect inventory count, or attempting to dispense an item that's already gone, ensures atomicity of the inventory update.
Synchronized decrement count on the slot. And the items.
The item, like cola or chips, should be an immutable DTO, holding its name and price constant.
Immutable item. Okay, state pattern king, the vending machine. Time for some games. Let's dive into blackjack and a deck of cards. modeling a generic deck plus the specific game. Emphasis on separating concerns.
Okay, blackjack. For the participants, dealer and player would use inheritance, extending an abstract participant class. This base class could hold common things, like their hand of cards. The blackjack game itself uses composition. It's composed of a deck, a dealer, and a list of players. These are essential parts of the game. Similarly, hand and deck are composed of card objects. Cards belong to hands and decks.
How about the dealer's logic? Hit on 16, stand on 17, etc. House rules vary.
That's a perfect fit for the strategy pattern. You define an idealer play strategy interface. Concrete strategies like hit and soft 17 strategy or stand on 17 strategy encapsulate the specific decision-making logic. The dealer object holds a reference to one of these strategy objects. This allows you to change the house rules just by plugging in a different strategy object without modifying the dealer class itself.
Where RG for dealer AI, very neat. And the cards, suits, ranks.
Suits, hearts, diamonds, etc. And rank 2, 3, king, AC should definitely be enums. This provides tyke safety. The rank enum should also have associated blackjack value attributes. Example, 10, jack, queen, king all have value 10. AC can be 1 or 11.
Enums for suit and rank with values. Now the deck. Dealing cards needs to be fair and correct, especially if you imagine a multi-threaded game environment, maybe online poker. How's the deck handled?
The deck's deal method, or deal card, should be synchronized. This prevents multiple threads from trying to draw cards simultaneously, which could mess up the order or lead to dealing the same card twice. Ensures atomic dealing. Internally, the deck might use a concurrent link deck to hold the cards. This is a thread-safe collection, ideal for representing a deck where you're typically adding card moving from one end, dealing, or maybe shuffling.
Synchronized deal, maybe a thread-safe collection. And the card itself.
The card object, representing, say, the ace of spades, must be immutable. Its suit and rank should never change once it's created. Ensures consistency throughout the game's lifetime.
Immutable card. Okay, let's order up some design for a food delivery system, like DoorDash. Uses Observer to update parties on status. Strategy for fees payments. Sounds familiar.
Yeah, lots of common patterns reappear. The core here is the observer pattern. The order object is the subject. Customer, restaurant, and driver act as observers, implementing iOrderObserver. When the order status changes, order status.preparing, it automatically notifies all its registered observers by calling their update method. Keeps everyone in sync in real time.
Observer for status updates. Who are the users?
Customer, driver, and restaurant manager would likely use inheritance from an abstract user-based class. A restaurant has a composition relationship with its menu, and the menu is composed of menu items.
And the order itself.
An order forms an association linking a customer, a restaurant, and eventually a driver. Ties them together for that specific delivery.
Pricing and payments.
You'd use the strategy pattern again, an iDelivery fee strategy interface for calculating delivery costs based on distance, time, etc., and implicitly, a payment service likely uses iPayment strategy for handling the actual payment.
What about matching restaurants' orders with drivers? That seems complex.
That's where the mediator pattern comes in handy. An order dispatch system acts as a mediator. It sits between restaurants with ready orders and available drivers. It handles the complex logic of finding the best driver for an order, assign driver to order, decoupling restaurants and drivers from needing direct knowledge of each other's status or location algorithms, centralizes the matching logic.
Mediator for dispatching.
Okay.
For a real-time system tracking locations and order status. What about thread safety?
The location service is critical, just like in ride-sharing. It needs to use a concurrent hash map for driver locations and maybe restaurant locations too. Ensures thread-safe updates and lookups as drivers move and restaurants update their status.
Concurrent hash map for locations again, and tracking the order's journey.
An order status enum is essential. It needs to be detailed enough to cover the whole life cycle. Pending, accepted by restaurant, preparing, ready for pickup, picked up, out for delivery, delivered, canceled. Provides type-safe and clear state transitions.
Detailed order status enum. Got it. Okay, from food to finance, let's look at the online auction system. Combines state and observer for life cycle and bid notifications, and critical thread safety for bidding.
Right. The auction object is the subject in the observer pattern. It notifies subscribed bidders, who implement iBidder, whenever a new high bid is placed, maybe via an on new high bid. method keeps everyone informed. Simultaneously, the auction is also the context for the state pattern. It holds an auction state, e.g., pending state, active state, closed state, canceled state.
State pattern controls what can happen when.
Exactly. For instance, bids can only be placed, place bid method, if the auction is currently in the active state. The state object enforces these rules, prevents bidding before the auction starts or after it ends.
Okay. Who are the participants?
Seller and bidder would inherit from an abstract user class. The auction has an association with the item being sold and the seller. It also has a composition of bids. The bids are integral parts of the auction's history. An auction service might act as a facade to simplify creating auctions, searching options, or placing bids for clients.
Observer for notifications, state for life cycle control. Now, bidding can be fierce. Fractions of a second might matter. How do we ensure thread safety when multiple users slam bids at the same time?
This is absolutely paramount for fairness and correctness in an auction. The auction.placebid bid method must be synchronized.
Synchronize the place bid method itself.
Yes. This ensures that only one bid is processed and evaluated against the current highest bid at any given moment. It prevents race conditions where two bids arriving nearly simultaneously might both appear higher than the previous bid but lower than each other, leading to an incorrect outcome. The synchronized method then delegates validation. Is the bid amount valid? Is the auction active? To the current state object.
Critical synchronization for place bid and the bid object itself.
A bid should be an immutable DTO. It represents a single bidding action capturing the bidder id, bid amount, and timestamp at that exact moment. Being immutable ensures its integrity once created and recorded.
Immutable bid and the auction status.
An auction status enum is typically managed internally by the state pattern to track the auctions phase, pending, active, closed, etc., in a type-safe way.
Got it. Synchronized bidding, immutable bids. Okay, let's check into the hotel management system, core operations, booking, room management, guest services.
The main hotel class often acts as a facade, providing that simplified entry point for users, guests, or staff to search rooms, make bookings, check-in, etc., hiding the underlying room inventory and booking logic. For creating rooms, the factory pattern is very suitable. A room factory can create different types of rooms, standard room, deluxe room, suite, based on input. These concrete room types would inherit from an abstract room class, useful for setting up the hotel initially.
Factory for room creation. What about pricing? Hotels often have dynamic pricing.
Yep, perfect for the strategy pattern. An iPricing strategy interface allows different pricing models: seasonal pricing, weekday pricing, loyalty member pricing. The booking system uses the appropriate strategy to calculate the room rate.
Strategy for pricing. Users.
Guest and various staff roles, G, receptionist, manager, would use inheritance from an abstract user class. The hotel has a strong composition relationship with its rooms. Rooms are integral parts of the hotel, and a booking forms an association linking a guest to one or more rooms for a specific duration.
Okay. Room availability is obviously central. How is inventory managed safely with multiple guests or receptionists trying to book or check in out concurrently?
You'd likely have a room inventory class or similar responsible for managing the status of all rooms. All its operations that modify room availability methods like check-in room, reserve, roomid, dates must be synchronized.
Synchronize all those key inventory operations.
Absolutely essential. This prevents catastrophic double booking errors. Imagine two receptionists simultaneously trying to check a guest into the last available suite. Synchronization ensures only one succeeds, and the room status is updated atomically.
Critical synchronization on inventory. Other structural elements.
A separate booking service could handle reservation logic, SRP. Booking itself should be an immutable DTO once confirmed, and you'd use enums like room status, available, occupied, maintenance, cleaning, and room type, standard, deluxe, suite, for type safety.
Immutable booking, synchronized inventory. Got it. Time for another game. The chess game. Models the game with complex move validation and that detailed piece hierarchy.
Right. Piece is an abstract class, and concrete pieces like pawn, rook, knight, bishop, queen, king use inheritance. They share common properties, like color, but have unique behaviors. The most complex part is move validation. This is brilliantly handled by the strategy pattern. Each concrete piece class has an I move strategy, knight move strategy, pawn move strategy, king move strategy.
So the movement logic is in the strategy object, not the piece object.
Exactly. This encapsulates the unique, complex move validation rules for each piece type cleanly. The piece object just delegates is valid move target square to its strategy object. Makes the system incredibly modular and easier to manage the complex rules of chess.
Strategy pattern for move validation. Very powerful here. How is the game board structured?
The game object is composed of a board and two players. The board itself is typically composed of a 2D array or similar structure of square objects. Each square has an optional association with a piece. It holds a reference to a piece if one occupies it, otherwise it's null.
A move itself.
Ah.
How is that represented?
A move object acts as a command DTO. It represents a single proposed action, typically containing the start square, end square, and perhaps the piece moved. It encapsulates the move request before validation.
Okay. How is the overall game flow managed? Making sure turns are respected, moves are legal.
The game class orchestrates this. Its make-move-move method is central. It first checks if it's the correct player's turn. Then it asks a piece on the start square if the move to the end square is valid, delegating to the piece's I-move strategy. If valid, it updates the board state, handles captures, checks for checkmate, stalemate, and switches the current player.
Game class orchestrates, delegates validation to piece strategies. What about tracking game state?
You'd use enums like color, white, black, for player sides and game status. In progress, white wins, black wins, stalemate, draw, for the overall game outcome. Ensures type safety.
Enums for color and status. Okay, sticking with games, let's simplify with tic-tac-toe. Simple game, but great for demonstrating core OOP and modularity, right?
Absolutely. Even tic-tac-toe highlights key principles. Encapsulation is fundamental. The board's grid, maybe a 2D array, and size are private. Access is controlled through public methods like make move and check winner, protecting the internal state. Abstraction is seen with player often being an abstract class. It defines the contract, make move, but hides the implementation details.
Which leads to
Inheritance. You have a human player that prompts for input, inheriting from player. This design makes it super easy to add an AI player later, maybe using a minimax algorithm, without changing the main game loop at all. Just plug in a different player object.
and the game uses that player object.
Yes, through polymorphism. The game loop just calls current player.makeMove. Whether current player is a human player or an AI player, the correct implementation gets executed.
How do game, board, and player relate?
Game has a composition relationship with board. The board is created and managed by the game. Its life cycle depends on the game. However, game usually has an aggregation relationship with players. The player objects might exist independently of a single game instance. For example, user accounts in a larger system. The game uses players, but doesn't necessarily own them exclusively.
Composition for board, aggregation for players, nice distinction. Any other key elements?
Enums are crucial for mark, X, O, empty Y, and game status, playing XW ins, OINs, draw for type safety, and using the final keyword for immutable fields like the board size or a player's assigned playing mark X or O is good practice.
And the game flow itself.
The game class runs the main loop. Get move from the current player, validate the move is the square empty, apply the move to the board, check if the move resulted in a win or a draw, and if not, switch the current player. Pretty straightforward loop. A move object, row, cold mark, could be used as an immutable DTO.
Clear and modular. Okay, next, the childhood classic, snake and ladder game. How do we design this board game effectively using OOP?
This design uses inheritance quite effectively for the board elements. Snake and ladder both inherit from an abstract class called jumper. This jumper class defines the common properties, start position and end position. This simplifies board setup and allows you to treat snakes and ladders polymorphically when checking a cell.
Inheritance for jumpers. What about the game structure?
The game class is composed of a board and dice, or a single die, using composition. The board itself is implicitly composed of cells, though cell might not need to be an explicit class here.
How are player turns managed?
A queue, like linked list or array deck, is the perfect data structure for managing player turns in the game class. You add players to the queue, and each turn you dequeue a player, let them play, and then enqueue them again at the end. Naturally handles the round-robin turn rotation.
Queue for player turns. How does the board know about snakes and ladders?
The board class often uses a map, example, hashmap integer jumper, to store the jumper objects keyed by their start position. This allows for very efficient lookup. When a player lands on square X, you just check if jumper map contains key X.
Map for efficient jumper lookup. Any other OOP features?
You might see constructor overloading in the game class, allowing it to be initialized in different ways, either default board size and dice or custom ones. And the snake and ladder constructors would use the super keyword to call the parent jumper constructor to initialize the start and end positions.
And the key game logic pieces.
The board.getNext position, current position, dice value method, calculates the raw next position and then checks the jumper map. If a jumper starts at that position, it returns the jumper's end position. Otherwise, it returns the calculated position. The dice.roll method encapsulates the logic for generating a random dice outcome, for example, 1 to 6.
Straightforward logic. Moving into modern digital infrastructure, file storage system like Google Drive or Dropbox.
This design is a classic application of the composite pattern.
Composite, how does that apply here?
You have an isStorage item interface, the component, both file, a leaf node, and directory, a composite node, which can contain other storage items, implement this interface. This allows clients, like the UI or other services, to treat individual files and directories containing other directories and files uniformly. For example, calculating the total size, get size, a file just returns its size, while a directory recursively calls get size on all its children and sums them up. Same interface, different behavior.
Uniform handling of files and folders. Very elegant. What manages the overall system?
The file system class often uses the singleton pattern to ensure only one instance exists, acting as the main entry point. It also acts as a facade over the complex operations like creating files directories, deleting, moving, searching, etc.
Singleton facade for the file system. How are permissions handled?
You'd have an association involving a permission class, linking a user and an isStorage item. This defines who can do what, read, write, delete, to which file or directory. File and directory also typically have an association back to their parent directory. The design emphasizes high cohesion, classes do one thing well, and low coupling, classes interact through interfaces like a storage item.
Composite. Singleton. Facade. Now, security and concurrency are huge for a shared file system. Multiple users accessing, modifying, deleting. How are permissions enforced and thread safety handled, especially within directories?
The Access Control List, ACL, often implemented as a map user, permission type within or associated with each isStorage item, is critical for enforcing those permissions. Before any operation, the file system would check the ACL. For concurrency, the directory class needs to handle modifications to its list of children safely. It should use a concurrent hash map to store its children, mapping name to isStorage item.
Concurrent hash map for the directory's children. Why?
Because you could have multiple users simultaneously trying to create files, delete files, or rename files within the same directory. Concurrent hash map allows these operations to happen concurrently with fine-grained locking, preventing corruption of the directory structure without locking the entire directory for every single read operation. Methods like add entry, remove entry on the directory would operate safely on this concurrent map.
Concurrent hash map for safe directory modifications. Crucial. Okay, from files to flight. Airline reservation system. A complex domain model represents real-world entities and their intricate relationships.
Yes, this one showcases how OOP models complex domains. You see complex associations like many-to-many or one-to-many. A key example is the distinction between flight, the abstract route for LHR to JFK, and flight instance, a specific occurrence of that flight on a particular date and time. A flight can have many flight instances. We see composition again. A booking has a payment associated with it. An aircraft, the physical plane, is composed of seats.
Payment.
iPayment strategy interface using the strategy pattern allows different payment methods. The system uses a rich domain model. Classes like flight, flight instance, airport, aircraft, seat, passenger directly mirror real-world aviation concepts, capturing their attributes and relationships accurately.
High fidelity model. How are things kept clean?
Encapsulation protects internal state, like a seats is booked status, accessible only via methods like book or cancel booking. The design aims for high cohesion, classes have focused responsibilities, and low coupling. An airline service often acts as a facade to simplify high-level user operations like searching flights or managing bookings.
Okay, rich model. Now the critical part. Booking seats on a specific flight instance. Concurrency is absolutely vital to prevent overbooking the flight. How is that handled?
First, the aircraft class, which defines the physical seat layout, for example, 1A, 1B, 20F, is often designed as an immutable object. The physical layout of the plane doesn't change. The crucial concurrency control happens in the flight instance class. Its reserved seat, seat number, passenger ID method must be synchronized.
Synchronize the reserve seat method on the specific flight instance.
Yes. This prevents race conditions where multiple users or agents simultaneously try to book the same seat on that specific flight. By synchronizing, you ensure that only one thread can check seat availability and change its status to booked at a time. Guarantees a seat is sold only once.
Critical synchronization for reserve seat. What about the seat itself?
Seat should be an immutable DTO, primarily holding its identifier, like 14C, and maybe its seat class, economy, business first. Seat class and seat status, available, booked, reserved, would be enums for type safety.
Immutable seat, synchronized reserve seat. Okay, next up. The shopping cart system. Models a standard e-commerce flow separating products, cart, and order concerns. Seems related to the earlier e-commerce example.
It is, but focuses perhaps more tightly on the cart and checkout aspect. Again, member and guest might extend an abstract user using inheritance. A user or user session is typically composed of a shopping cart using composition. The cart belongs to the user session. A cart item within the cart has an association with a product in the catalog. It links the item in the cart with quantity to the actual product details. An order contains a list of order items. This is more like aggregation association, because the order item captures product details at the time of purchase but references the product.
How is the cart managed internally?
The shopping cart often uses a map, for example, hash map product ID, cart item, for efficient management, allows quick lookup, update quantity, or removal of items based on the product ID. A checkout service acts as a facade, coordinating the steps, maybe locking cart items, reserving inventory, processing payment, and finally creating the persistent order.
Okay. What are the absolute key thread safety and immutability points for the shopping cart, especially considering prices can change?
Right. First, all methods that modify the shopping cart's contents, add item, update item quantity, remove item, clear cart, must be synchronized on the cart object.
Synchronize all cart modifications. Why again?
Because the cart is usually tied to a user session, and concurrent actions from that user, for example, multiple tabs, rapid clicks, adding, removing items, could lead to inconsistent state, wrong quantities, wrong total, if not synchronized, ensures atomic updates to the cart. Second, and crucially, order item must be an immutable DTO, and it absolutely must store the price at purchase.
That point again, why is it so stressed?
Because it's fundamental to correctness in e-commerce. The product's price in the main catalog can change at any time. If the order item just held a reference to the product, the price charged at checkout could be different from the price shown when the item was added to the cart. Storing price purchase in the immutable order item guarantees the price is fixed at the moment of commitment, adding to order checkout, and ensures historical order accuracy.
Got it. Immutable order item with price purchase is non-negotiable. What about product?
Product itself is often best treated as an immutable DTO. At least its core identifiers like protected should be final. Its price might be stored elsewhere or handled carefully, if mutable.
Okay, clear. Let's delve into the high-stakes world of finance. The online stock brokerage system handles different order types: market, limit, real-time data, portfolio management. Concurrency here must be paramount.
Absolutely. For different order types, the strategy pattern is key. An I-order execution strategy interface defines how orders are filled. Concrete strategies like market order strategy, fill at best available price, and limit order strategy, fill only at specified price or better, encapsulate the execution logic. The order object is composed of one of these strategies.
Strategy for order execution. What coordinates the market?
The exchange acts as the central marketplace, often implemented as a singleton to ensure there's only one global venue for order matching. User accounts. Account would likely be an abstract class, demonstrating inheritance and abstraction. Concrete types like cash account or margin account could inherit from it, potentially having different place order logic or risk checks. A brokerage service acts as a facade, simplifying user interactions like placing orders, viewing portfolios, depositing funds.
Okay, now the absolute core, the real-time order matching engine. How is this designed to be thread-safe and handle potentially thousands of orders per second accurately? This is where concurrency is make or break.
You're right, this is the most critical part. The order book for each stock is the heart of the matching engine. It needs to be highly efficient and perfectly thread-safe. Internally, it typically uses two priority queues. One for buy orders, usually a max heap ordered by highest price first, then time, and one for sell orders, a min heap ordered by lowest price first, then time. This structure naturally supports the price-time priority matching algorithm.
Priority queues for buy-sell orders. How is matching kept safe?
The match orders method or similar logic triggered when a new order arrives within the order book must be protected by a lock, typically a reentrant lock.
Reentrant lock on the matching logic.
Yes, lock.lock. Before trying to match, lock.unlock in a finally block after. This prevents race conditions where multiple incoming orders might try to match against the book simultaneously, potentially leading to incorrect fills, partial fills being missed, or the order book state becoming corrupted. Order matching must be atomic for a given stock.
Critical lock-around matching. What about user accounts when placing orders?
The account methods like place by order and place sell order, which would check fund holdings and update them, also need to be synchronized on the specific account instance. This ensures atomic updates to the user's cash balance and portfolio holdings when an order is placed or filled.
Synchronized account methods and order types.
An order type, enum, market, limit, stop, etc., ensures type safety.
Priority queues, reentrant lock for matching, synchronized account updates, very critical points. Okay, from stocks to spending. Digital wallet service, like PayPal or Venmo, focus on security, transaction management, notifications.
The wallet object itself often acts as the central subject in the observer pattern. Observers implementing an iWallet listener interface, for example, transaction logger, UI notifier, fraud detector, can register with the wallet. When an event occurs, like on transaction complete, on transaction failed, on funds added, the wallet notifies all its listeners, keeps different parts of the system updated.
Observer for wallet events. How are different payment sources handled? Bank accounts, credit cards.
You'd use an interface, maybe iFinancial instrument. Classes like bank account and credit card would implement this interface. This promotes polymorphism. The wallet can interact with any financial instrument through the common interface methods, for example, charge amount or deposit amount.
Interface for financial instruments. Transaction types.
The debit transaction and credit transaction could use inheritance, extending a common abstract transaction class that holds shared properties like amount, timestamp, status. Encapsulation is key for the wallet's balance. It should be private and only modifiable through controlled, synchronized methods.
And a relationship.
A wallet is associated with a specific user and holds a list of associated financial instruments.
Okay. Now, financial transactions demand perfect accuracy and atomicity. How is thread safety ensured when sending money or adding funds, potentially concurrently?
All methods within the wallet class that modify the balance, like send money, recipient wallet amount, or add funds, instrument amount, must be synchronized on the wallet instance.
Synchronize all balance-changing methods.
Absolutely. This guarantees atomicity. It ensures that the entire operation, ROG, checking balance, deducting amount, potentially crediting another wallet, happens as a single indivisible unit. Prevents race conditions where concurrent transactions could lead to incorrect balances, Farag overdrafts that shouldn't happen, double spending. Financial integrity depends on this.
Critical synchronization for balance updates. What about the transaction record itself?
The transaction object should be an immutable DTO. It captures the complete context of a financial event, from wallet to wallet, amount, type, status, timestamp. Being immutable ensures that once a transaction is recorded, its details cannot be altered, providing a reliable audit trail.
Immutable transaction DTO for audit trail and states.
Transaction status, pending, completed, failed, canceled, and transaction type, debit, credit, funding, would be enums for type safety and clarity.
Got it. Let's step into the fast-paced environment of a restaurant management system. Uses Observer to decouple front of house, waiters, tables, from back of house kitchen. Waiter acts as a facade.
Exactly. The order object acts as the subject in the observer pattern. The kitchen display system, KDS, is a key observer. When a waiter confirms an order, order.setstats, order status.confirmed, the order notifies its observers, including the KDS, via maybe an on new order received order method. This makes the order instantly appear on the kitchen screen.
Observer sends orders to KDS. What about the KDS itself?
The kitchen display system is typically a singleton, as there's usually only one central KDS for the kitchen.
Roles, waiters, chefs, menu items.
You'd use inheritance and abstraction, an abstract employee-based class for waiter and chef, an abstract menu item-based class for specific food item and beverage item classes. An order aggregates order items using aggregation. The order is made up of items.
And the waiter's role.
The waiter often acts as a facade for customers sitting at a table. The customer interacts primarily with the waiter for taking orders, requesting the bill, making payments. The waiter then interacts with the more complex systems, or order system, KDS, payment system, simplifying things for the customer.
Waiter as facade. Okay, how do we ensure the KDS handles potentially many orders coming in concurrently from different waiters and track statuses correctly.
Since the kitchen display system is a singleton, its on-new-order-received method, or similar, needs to be synchronized. This prevents race conditions if multiple waiters submit orders at the exact same time, ensuring orders are added to the kitchen's queue consistently. Internally, the KDS would likely use a queue, perhaps a concurrent linked queue, to hold pending orders for the chefs to process in FIFO order.
Synchronized KDS method, internal queue. Any other concurrency hints?
The order status attribute itself might be marked volatile.
Volatile on the order status? Why?
To ensure visibility. If a chef updates the order status on the KDS, example preparing, volatile helps ensure that other threads, maybe a status tracking service or the waiter's handheld, see that change promptly, preventing stale status reads.
Volatile for status visibility. And states.
Table status, free, occupied, reserved, and order status, received, preparing, ready, served, paid, would be enums.
Got it. Now for the academic world. The course registration system. Mirrors university operations. Distinguishes abstract courses from concrete offerings. Seems complex.
It is, and a key aspect is that clear abstraction. The difference between course, the abstract concept, e.g. CS 101 Intro to Programming, and course offering. A concrete instance of CS 101 offered in fall 2024, MWF 10 a.m. by Professor Smith with a capacity of 50. This distinction is crucial for accurately modeling how universities work and avoiding data redundancy.
Abstract course versus concrete course offering. Who manages these?
A course catalog often acts as a singleton. It's the single source of truth for all available courses and their specific course offerings each semester. Ensures consistency across the system.
Singleton course catalog. What are the relationships?
It's a rich model with many associations. Student registers for course offerings. A course offering is associated with one course and one professor. A course belongs to a department. Encapsulation is important too. A course offering encapsulates its own registration logic, checking prerequisites, checking if capacity is reached, adding or removing students from its roster.
Course offering manages its own enrollment. How are things accessed?
Maps are useful. A student might have a map semester, list course offering for their registered courses. The course catalog uses maps to quickly find courses or offerings. A registration system might act as a facade to coordinate the overall registration process between a student and the catalog offerings.
Okay. Now, course registration is notorious for registration wars. Huge numbers of students hitting the system simultaneously trying to get into popular courses. How is concurrency handled to prevent over-enrollment or other chaos?
Concurrency is absolutely critical and often a major pain point in real university systems. The key registration methods must be synchronized.
Which method specifically?
On the student side, methods like register for course offering and drop course offering. And crucially, on the course offering side, methods like add student and remove student.
Synchronized methods on both student and course offering.
Yes. Synchronizing add student on the course offering instance is vital to prevent over-enrollment. It ensures that the check for available capacity and the actual addition to the roster happen atomically. Without it, two students could simultaneously see one spot left, both try to register, and both succeed, exceeding capacity.
Critical synchronization on course offering.addStudent.
And synchronizing on the student methods prevents issues like a student concurrently registering for two conflicting time slots or exceeding their maximum credit limit due to race conditions. The course catalog.getInstance method, if it does initialization, should also be synchronized.
Rigorous synchronization needed. Okay, let's browse through the online bookstore, a specialized e-commerce system for books, focused on search, inventory, checkout.
Right. This involves domain-specific modeling with classes highly tailored to the book world. Book, author, publisher, ISBN, genre, review. The bookstore class might demonstrate method overloading for its search methods. You could have search string title, search author, author, search string as per ISBN, providing flexible search options with the same method name.
Overloaded search methods. Other relationships.
A book aggregates reviews using aggregation. Reviews are related to the book but might be managed separately. The final keyword is important. Order item could be a final class, cannot be subclassed, to enforce its immutability. The ISBN within a book object should definitely be a final field. It never changes.
Use of final. What about comparing authors?
Good point. It's important to remember to override equals and hash code in classes like author and maybe publisher if you intend to use them as keys in maps or store them in sets to ensure correct behavior based on value equality, not just object identity.
Override equals in hash code. How is the system structured for clarity?
It should aim for high cohesion and low coupling. For example, an inventory class solely manages stock levels, decoupling it from the search service or the shopping cart. The bookstore class itself likely acts as a facade for the primary user workflows: search, view book details, add to cart, checkout.
Okay. Maintaining accurate stock counts and pricing is vital, especially with potentially many users browsing and buying. How are these handled safely?
The inventory class needs thread-safe stock management. Again, using atomic integer within a map SBN, atomic integer for stock by SBN is a good approach for efficient atomic updates to stock counts. The add book method, if modifying shared structures, might also need synchronization. The search service would benefit from the strategy pattern using an iSearch strategy interface for different search algorithms. Search by title, search by author, search by ASBN, maybe search by genre, makes it easy to add new ways to search.
Strategy for search again? And the order items, price changes.
Just like the general e-commerce system, order item must be an immutable object and must store the price purchase. Protects against price changes after adding to cart, ensures order accuracy. Book itself is also best designed as an immutable DTO.
Immutable book and order item with stored price.
Got it. Now for the vast landscape of a social media platform, generic. Flexible foundation for services like Twitter, Instagram, Facebook, focus on content, feeds. Right, a generic base. You'd use inheritance and abstraction heavily. A post-abstract class provides a template, author, timestamp, likes, comments. Concrete types like text post, image post, video post inherit from it. This allows polymorphism. You can have a list of post objects, and when you call display on each one, the correct implementation for rendering a text post, image post, etc. gets executed.
How are posts created?
The factory pattern is useful here. A post factory can create the appropriate post object, create text post, create image post based on input. This decouples the user class, who initiates the post, from the specific creation logic of different post types. Easy to add new types like poll post later.
Factory for post creation. What about the news feed? That's complex.
Yes, the complex logic for generating a user's newsfeed is hidden within a newsfeed service good encapsulation. And representing the social graph, followers, following. Using maps or sets like set user AD followers, set user ED following provides efficient O1 lookups for checking relationships, which is essential for quickly finding posts from followed users when generating the feed.
Efficient graph representation. Now, the feed generation itself and user interactions like liking concurrency concerns.
Feed generation is complex. The newsfeed service would likely use the strategy pattern with an iFeed generation strategy interface. Different strategies, chronological feed, relevance feed, algorithm X feed, could be plugged in to rank and assemble the posts for a user's feed. This is core to how platforms customize feeds.
Strategy for feed algorithms. What about likes? Many people liking concurrently.
The post.addLike method, or similar counter methods like increment comment count, needs to be synchronized. This ensures thread-safe updates to the like count, preventing lost likes due to race conditions from simultaneous actions.
Synchronize add like and comments.
A comment object should be an immutable DTO. Once posted, its text and author shouldn't change. A post-type enum could be used by the factory.
Immutable comment. Okay, let's get more specific with Facebook, an advanced social media platform. Extends the generic model with groups, pages, events, complex reactions.
Right, Facebook adds layers. Member might be a specialized type of user using specialization, inheritance, adding profile details, relationship status, etc. It models very rich graph-like relationships using complex associations between members, groups, pages, events, posts, etc. A member can join multiple groups, like multiple pages, RSVP to events.
How are specific features like reactions or group privacy handled?
Through data-rich enums. Reaction type would be an enum, like love, haha, wow, sad, angry. Group privacy would be an enum, public, private, secret. Using enums makes the code type-safe, readable, and self-documenting. The design promotes high cohesion. Classes like group manage their own members, posts, and privacy settings. Event manages its attendees and details. Encapsulates specific logic. And low coupling. A member interacts with an event via a clear interface like RSVP or RSVP status without needing to know the internal details of how the event manages attendance.
Okay. Facebook deals with a massive volume of interactions. How are stateful things like friend requests managed? And thread safety for those complex reactions.
A friend request is nicely modeled as a stateful object. It would have a request status enum, pending, accepted, declined, ignored, and methods like accept and decline that transition its state. This mirrors the real-world workflow better than just simple flags.
Stateful friend request, object, and reactions.
The post.addReaction user add reaction type method needs to be synchronized. It's updating shared counters for each reaction type associated with the post. Synchronization prevents race conditions and ensures accurate reaction counts when many users react concurrently.
Synchronize add reaction? Any other enums?
An event RSVP enum, going, interested, not going, would manage attendance status for events.
Got it. For our penultimate system, let's step onto the cricket pitch with Cricinfo live sports commentary. Highly domain-specific, real-time. Focus on the hierarchical structure of a cricket match.
Yes, this one is all about modeling the domain accurately. It features a deep composition hierarchy, which is essential for cricket. A match is composed of innings. An innings is composed of overs, and an over is composed of balls. This precise nested structure ensures data integrity and perfectly mirrors the logical flow and containment of the game.
Deep composition hierarchy. How are live scores delivered to viewers?
The observer pattern is vital. The match object, or maybe an innings object, acts as the subject. Various viewers, iLiveScore viewer implementations like mobile app viewer, website viewer, TV graphics system act as observers. When a significant event happens, like match.addBall, ball data, the match object notifies all its registered viewers via an update score method, ensures everyone sees the latest score, commentary snippets, etc. in real time.
Observer for real-time score updates. Other relationships.
Player might aggregate player profile, stats, history, using aggregation. And you need lots of domain-specific enums. Match type, test, ODI, T20, wicket type, bowled, caught, LBW, run out, stumped, etc. Ball type, normal, wide, no ball, bye, leg B. These make the system robust, type-safe, and easy to understand for developers familiar with cricket.
Rich set of enums. Now, for live commentary, the accuracy and immutability of past events seem critical. You can't change what happened on a previous ball. How is that ensured?
Absolutely crucial. The ball object, which represents the outcome of a single delivery, runs scored, extras, wicket details, must be an immutable DTO. Using final class and fields is typical.
Immutable ball DTO. Why is that so important?
Because it guarantees that once an event has happened and been recorded, a specific ball was bowled with a specific outcome, that record cannot be altered accidentally or maliciously later. This immutability is essential for historical accuracy, generating statistics, and maintaining the integrity of the live commentary feed.
That makes perfect sense for sports data. What else?
A wicket object, if used, would also be an immutable DTO. And the match.addBall method, or wherever the central state update happens, should be synchronized. This handles potentially concurrent updates coming from data feeds or scorers, ensuring the match state, score, overs bowled, wickets down, is updated atomically and consistently.
Synchronized add ball, immutable ball, and wicket. Key for live sports. Okay, finally, let's look at the API rate limiter. Critical infrastructure component. Uses strategy pattern, focus on thread safety for the core algorithms.
Right. The strategy pattern is central here. An iRate limiting strategy interface defines the contract for checking if a request should be allowed. Concrete implementations encapsulate different algorithms. Token bucket strategy, leaky bucket strategy, fixed window counter strategy, sliding window log strategy. This allows the rate limiter service to use different algorithms easily, perhaps even different ones per user or API endpoint, just by plugging in the appropriate strategy object.
Strategy for limiting algorithms. How are these strategies chosen or created?
A token bucket factory, or a more general rate limiting strategy factory, could use the factory pattern. It might create specific iRate limiting strategy instances for users based on their subscription tier, e.g., free users get a stricter limit than premium users. Subscription tier itself would likely be an enum, free, basic, premium, possibly holding the specific requests per minute or other parameters associated with that tier.
Factory based on subscription tier enum. And the service itself.
The rate limiter service acts as a facade. Clients, like an API gateway, just call a simple method like isAllowed user in on the service. The service then signs a rate strategy for the user and delegates the check to it.
Facade for the service. Now, the algorithms themselves, token bucket, leaky bucket, etc., need to track state, tokens, timestamps. How is thread safety ensured? Multiple requests for the same user can arrive concurrently. This seems like a really tricky concurrency problem.
It is, and it's absolutely critical to get right. Let's take the token bucket strategy as an example. Its isAllowed method must be thread safe. Usually this means the method itself is synchronized, or it uses an internal reentrant lock.
Synchronize is allowed. In the token bucket. Why?
Because multiple requests for the same user can hit the rate limiter concurrently. The logic involves checking the current token count, potentially replenishing tokens based on the time elapsed since the last replenishment, and consuming a token if available. This entire sequence, check, replenish, consume, needs to be atomic for that user's bucket. Without synchronization, two threads could simultaneously see one token available, both try to consume it, and you'd allow 2 requests when only one should have passed. Synchronization prevents this race condition.
Atomic check, replenish, consume. What about the internal state variables?
The token bucket strategy might use atomic integer for current tokens for efficient atomic updates, especially under high contention. The last refill timestamp should be volatile to ensure that updates to this timestamp, when tokens were last added, are immediately visible to all threads checking the same bucket, preventing stale reads and ensuring accurate replenishment timing.
Atomic integer for tokens, volatile for timestamp, synchronized is allowed method, robust concurrency for rate limiting. Got it. Hashtag tag outro. Wow, okay. That was an intensive deep dive. We've just rapidly dissected, 34 distinct system designs, unpacking their core OOP principles, the key design patterns, and those absolutely crucial points about multi-threading and thread safety.
Yeah, we covered a lot of ground. From the simple elegance of a singleton ensuring one entry point in the parking lot,
Right.
to the really robust synchronized bidding logic needed to prevent chaos in an online auction.
And the power of immutable event records, like in the Crisinfo example, ensuring data integrity for live commentary.
Yeah.
You should now have this really formidable mental toolkit ready.
Definitely. And this wasn't just about listing patterns, was it? It was about getting the why.
Exactly. Why choose this pattern here? Why is thread safety non-negotiable in that specific scenario? How do these fundamental OOP principles actually bring order and maintainability to what seem like incredibly complex problems? You basically now have a comprehensive low-level design playbook, specifically tuned for what interviewers are looking for in those Java OOP design rounds, packed with the reasoning they want to hear.
So as you go forward, armed with all this concentrated knowledge, here's something to chew on. How might these very precise design choices, like using atomic integer versus synchronized, or choosing composition over aggregation, how might those impact debugging, or even the long-term cost of maintaining a truly massive distributed version of one of these systems?
Or maybe, how could you combine patterns from, say, the notification system and the rate limiter to design something completely new?
The real power comes from applying and adapting these concepts. Keep exploring, keep asking why, and definitely keep designing. You're not just informed now, you're genuinely well-equipped.